Hello Legacy students, this is Miss Marsh speaking. Today we're going to look at proportions and similar figures, which is basically a reason for why we're learning how to solve proportions. I can use your learning goals. I can use proportions to solve a problem that involves similar figures. Now, what is similarity? This is something that comes further when you go to geometry next year. So we're going to take a quick look. So similarity, is a bear similar to a monkey? Well, of course not. They're not even the same thing. Is this butterfly the same as that butterfly? Yeah, they're similar, right? They look almost alike, not different in shape, or they're the same color, it even looks like. What about these two triangles? Well, they're the same shape, right? So they're similar. But these two shapes, they're not the same, so they're not similar. So what we look at is what's known as similar triangles. So similar figures is basically a figure that have the same shape but not necessarily the same size. So if I look at this, are these two heads similar? Are they the same shape? Not really, because they're not exactly the same shape. So here's what we're going to call a similar figure. Basically, they're exactly the same shape, but not necessarily the same size. So basically, they're going to look like either a blown-up version of each other, or one of them is going to be shrunk from the other one. Corresponding sides of these two figures are basically the same side. So if you would put them together and they would look the same side are corresponding. Corresponding angles are in the same position on your figure or your polygon. So let's take a look at this. I have two triangles below that are similar, and I need to find the length of side x. So I need to find this length here. So it looks like my two triangles are basically, they look the same, right? And I have a 6 here and a 4 here. Those are corresponding sides. So what we can do is set up our proportion. So I'm going to go big over small. So big triangle over small triangle. You're going to want to make sure that you do it that way for both of your ratios. You could go big over big and equal small over small. I find it's easier to go big over small. Alright? So my big side is 6, and the small side that corresponds to it is 4. So 6 over 4. Now, I need this x to somewhere get in there. So let's find the corresponding side to that x. Well, it's on this side of the 4, so it's got to be on this side of the 6. So 4.5 it looks like. So my big side, which is 4.5, over x. So now I need to find x. So let's solve this proportion. So same thing, cross product, 6x equals 4 times 4.5, 18 it looks like. Let's divide by 6. 18 divided by 6 is 3. So my answer would be 3. Alright, so we have these two triangles are similar. We need to find the length of D. So we need to find this right here. Notice though, my two triangles, they're not exactly orientated the same way. We need to think of it, what if they would be? What side matches up to what? Here's what's going to help you. Do you see how I have one little line over here and one little line over here? That is a geometer's way of saying these two angles are the same angle. Same thing over here. I have these two lines here and these two lines here. So what I can assume then is that this angle is the same as this angle. So A and P are the same thing. And I can assume C and Q are the same thing. That's going to help us figure out what sides relate to what. So if I want D, the side that relates to D, it looks like it's to the side of C, right? So it looks like it's got to be on 6. So D and 6 have to be related. So just like before, I'm going to go big over small. So I'm going to get 6 over D. Now, I need to find another proportion, right? Well, I can't use this side because that's C. So let's use this long side between B and A. So I'm going to use a different color here. Right here, I'm going to use 10. Now, what side on this triangle relates? Well, it looks like it's just the side right after the 6. So D was 6, so 5, right? So I got big over small. So 10 over 5. Let's find the other side. Let's find D. So 6 times 5 is 30. 10 times D is 10D. Let's divide here by 10. And I will get 3 equals D. I have found the side of my triangle that is missing. Now, be very careful when you have two shapes that are not in the same direction, I guess, if you want to call it that. You need to make sure you pay attention to what side matches to who. Now, why are we learning this? Why are we looking at similar figures? Well, this is really helpful for things that you can't actually measure. Like, I can't measure how tall the Empire State Building is with my measuring stick. That would take forever. So what you can use is what's known as indirect measurement. So basically, if two objects form right angles with the ground, so they're at 90 degrees or standing straight up and down, you can apply indirect measurements using their shadows. Let's take a look at what this looks like. So suppose I have this tree, this palm tree, and I want to know, will it fit inside my house? Well, I need to know this height of this tree then. So all I have is a tape measure, and you guys know how tall I am. I can't reach the top of the tree to figure out how long this is. And I don't want to try to climb it either. So I can measure the length of this tree's shadow, though. And I know his shadow is about 10 feet long. I know my shadow is 2 feet long. And I also know that I am 6 feet tall. So I can set up a proportion. So I can go the tree over me. Okay? So the tree is H, because I don't know it, right? Over my actual height equals the shadow of the tree over the shadow of me. So this allows me to solve my proportion of 2H equals 60. So I have my height of my tree is about 30 feet tall. Don't think it's going to fit in my house, guys. Probably not. So let's actually take a look at this. So a 6-foot student casts a 17 feet shadow. Let's assume we're probably at high noon. That's when your shadow is the longest. A tree casts a shadow of 102 feet long. Find the height of the tree. So I need to go, let's go tree over person or student. Right? So the tree, the actual height of the tree is H, and the actual height of the student is 6, right? Now, we gotta go tree, so the shadow of the tree we know is 102, and we know the shadow of the student is 17. So I was able to set up my proportion here. Let's go ahead and solve. So I'll go 17H equals 612, right? Yep, 612. Let's divide by 17. And it looks like 612 divided by 17 is 36. Oh, and I gotta make sure I label. 36 feet. So the tree is 36 feet tall. Let's take a look at a little bit more definitions. So proportions can use scale drawings or scale models. So if you've ever looked at like the scale car or ever looked down a hobby aisle and you find the scale cars that you can make out of various things, well, they say they're like 1 to 5 or 1/50th of the scale. This is what this is used for. This is how they actually find out how big the wheel should be. They use a scale model, or they find the scale of something. So sometimes it's like 1 inch is 0.5 meters, or 1 inch is 5 feet. Sometimes this is even on your normal maps. It will say how 1 inch is 5 miles or something like that. So that they don't have to draw a whole bunch, and they still, as a person, you can tell how long that actually is. So let's try a few examples. So a contractor has a blueprint for a house drawn to scale of 1 inch is 3 feet. So the wall in the blueprint is 6.5 inches long. How long is the actual wall? So we're going to go blueprint over actual, which is 1 inch over 3 feet. That's what we were told right here. So now we need to set up the rest here. So I'm going to keep that 1 over 3. Now, the wall on the blueprint is 6.5 inches long. So we need to follow the same proportion. So I got blueprint over actual. So on the blueprint, I had 6.5 inches over, I don't know the actual length. That's what I'm trying to find. So 1 times x is 1x, and 3 times 6.5 is 19.5. So my actual wall is 19.5 feet long. Not too bad, right? Oop. The actual distance between North Chicago and Waukegan, I want to say that is 4 meters. What is the distance, miles, excuse me. What is the distance between these two locations on the map? So we need to set this up. So we're going to go map over actual. Now, where did I get that 1/18th? If you look in the corner right here, sometimes that's where the map usually has it, in a corner. I'm told 1 inch is 18 miles. So that's where we stole that 1/18. So now let's use that to write the rest here. So I have 1/18 equals. Now, I'm told the actual distance from these two places is 4 miles. So I'm going to go over actual. I don't know the map. I want to know the distance on the map. So x over 4. Because we're going map over actual, right? So let's multiply. So I got 4 equals 18x. Looks like I got to divide by 18. So x equals 0.2 if I did that on my calculator right. And it looks like my map is in inches. So basically, on my map, the distance between these two maps is 0.2 inches. And that's the end of this video. See you later, Sabers.